Hello, Integrated Math 1. Welcome to lesson 1.2.4. It's our last lesson of this unit. I suppose it's a little sad, but you now know what you're doing. So we're just going to be taking this to the next level and playing with all the stuff that we've learned throughout this unit. So we do have a warm-up for you on page M1-143. I would like you to go ahead and write an explicit formula for each of these arithmetic sequences. You have already been told they're arithmetic, so that's convenient. Go ahead and hit pause to write down your lovely formulas and then hit play when you're ready to check your work. So to start off with, I knew this was arithmetic and I noticed that it was subtracting 1. I noticed that was my pattern. So when I went to fill in, I thought, okay, a few things. First of all, a sub 1 is my first term, which is 9. So I'm just making some notes here. I'm like, all right, so, where's my pen? Where's my pen? There's my pen. So I made some quick notes. I was like, okay, so there's my first term, so that's going to go here. Ooh, and subtract 1 means that your common difference is going to be a -1. I know you guys know that. People still keep making that mistake. It's very sad. So I'm just going to plug in those two. So I have a formula. So a sub n equals 9 minus 1 times n minus 1. Boom. We got a formula. So magical. For our next one, I noticed that it was actually going up. So we were adding this time, and it looks like we're adding 20. So it's definitely arithmetic still. So when I went to go use my explicit formula for arithmetic sequences, I was like, hey, there's my first term, a sub 1. And because we were adding 20, I was like, okay, so my common difference is a positive 20 this time. So I just plugged in the first term, plugged in the common difference, and I'm like, bam, there we are. Oh, they were both 20. Well, that's funny. So for the formula for this sequence, I have a sub n equals 20 plus 20 times n minus 1. And of course, these formulas are great because you can find any term in the sequence. You would just plug that in for n and be like, that's what the term is. It's pretty magical stuff. So I have a little activity for you guys today that we're going to play with. And we're just going to look at some scenarios and we're going to apply all of these formulas, arithmetic sequences, geometric sequences. We're just going to start like applying stuff. Yeah. So we are going to be modeling using sequences today. And our learning goals for today is just modeling situations that use recursive and explicit formulas, especially the explicit one. We're going to translate between recursive and explicit expressions of a mathematical model. What are these things and what do they mean? And we're just going to explore the process of mathematical modeling. That's what we are doing today. So I just have one key term, mathematical modeling. That's all it is. So that key term is going to pop up. So you've written recursive and explicit formulas for both arithmetic and geometric sequences now. So how can you model a real world situation using both recursive and explicit formulas for the sequences? That's what we're doing. So we're on page 144. In this lesson, we're going to explore the process of mathematical modeling. Mathematical modeling is explaining patterns in the real world based on mathematical ideas. So like, okay, we see a pattern, but how can we use math to explain that pattern? That's what we're doing. So in this lesson, you'll explore that process of mathematical modeling. And the first step in modeling a situation mathematically is to gather information, okay? Gather information, notice patterns, formulate mathematical questions about what you notice, right? That's our first step. So we're gonna play a little game. The object of the game is to move an entire stack of discs or coins from the start circle to any of the other circles. All right, so we're gonna have a stack and we need to move it from one circle to another circle, but there are rules. You can only move one disc at a time. True story. You can only move one disc at a time, okay? You can't grab a whole stack and move it. And here's the other trick. You cannot put a larger disc on top of a smaller disc. All right, so Let's first play with 3 discs. To begin, you can use coins. You can place a quarter, nickel, and dime on top of each other in that order in a stack in the start circle. Oh, mine's not in the start circle. Sorry, my bad. I will fix that. Hang on. Mine aren't in the right circle. I'm going to fix that. I'm going to move them around. Oh, there we are. Okay, boom. 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 Okay. That's better. So to begin, place a quarter, nickel, and dime on top of each other in that order in a stack in the start circle. So here's my lovely, I've got them all stacked up. Or if you don't have a quarter, nickel, and dime, there are cutout discs at the end of the lesson. That's what I've done. I've got my little cutout disc. So if you go over to page M1-151, you can cut out these circles to use them. So again, we're stacking them largest to smallest in the start circle. Boom. Yeah. So remember our rules. You can only move one at a time. You can only move one at a time. And you can't put a bigger one on top of a smaller one. So can you go ahead and hit pause? See if you can move all 3 of them, if you can get this whole stack to be on either the middle circle or the third circle. And see how many moves it takes you to do that. Can you just keep track of how many moves it takes you to do it? And if you can get it down as low as possible. I'm just saying, try it out. Go ahead and hit pause, play with this a little bit, and then hit play when you're ready to check and see how things are going, share information. So I'm going to play. Are you ready? I'm pretty good at this. I'm pretty good at this. So I'm going to take my middle circle. Ooh, it helps if I click on it, right? And I'm going to put it in the middle. So I'm going to take that top circle and put it in the middle. I'm now going to take my next biggest circle and I'm going to move it over to the end. So I just moved it over there. I need to move that guy over. So I'm going to move this little one on top of the medium-sized one. So I've done 2 moves so far, right? So 1, 2, 3 moves. Great. And that means I got to get this guy over. So 4 moves. Awesome. I can do this. 4 moves. I'm going to move this little guy over here. So 5 moves. Yep. Oh, we can do it now, right? 6 moves. 7 moves. Whew. I did it in 7 moves. I didn't put a big one on top of a little one. I got them all into a nice little stack in a different circle. If you ended up in the end circle, that's okay too. I ended up in the middle, but you may have ended up on the end. Either way is fine. But I managed to do it in 7 moves. Maybe you managed to do it. Maybe you took more. I don't know. I did it in 7. If you want, you can challenge yourself and try and see how many moves it takes with 4 or even 5 of these, because we do have 4 discs and 5 discs. You're welcome to play around with that a little bit, but I noticed it took me 7 moves to make that happen. So that's our first step in the modeling process. We're just moving things around. How many steps does it take? What do you notice? All of that good stuff. The second step in the modeling process is to organize your information and represent it using mathematical notation, right? Let's start using some numbers in there. So considering the question from the previous activity, is there a relationship between the number of discs and the minimum number of moves? So I would like you to play that game again, but can you play it with 1 disc and write down how many moves it takes? Can you then play it with 2 discs and write down how many moves it takes? And we already played with 3 discs and wrote down how many moves it takes. So see if you can do that, and then we're just going to record our results, and then we'll start moving from there. Go ahead and hit pause. How many moves for 1 disc? How many moves for 2 discs? How many moves for 3 discs? And then hit play when you're ready to check your work. I hope you realize that with 1 disc, it only takes 1 move. Yeah, with 1 disc, it only takes 1 move. 2 discs, it took 3 moves. And of course, we already noticed with 3 discs, it took 7 moves. So I was able to do 2 discs and 3 moves over, and on. Yeah. You know what? There might be a pattern here, though, right? right? I feel like maybe there's a pattern. Do you notice a pattern in the results? Can you write down what the pattern is on page 145 there on question 2? Can you write down your results? Go ahead and hit pause to write it down. Hit play when you're ready to check your work. So here's what I noticed. The minimum number of moves for 3 disks is 1 plus 2 times the minimum number of moves for 2 disks. Does that make sense? Maybe that didn't make sense. Here's my minimum. So 1 plus 2 is 3. I can say this. So it's 1 plus 2 times the minimum number. So I had to multiply this guy by 2 and then add 1. Maybe that was worded badly. Sorry. So I had to double this and then add 1. So double, add 1, double, add 1, double, add 1. Oh. With that in mind, is there a way that we can write that down that would help us identify our results a little better? Is there a way that we can write it as a formula? That's what I'm looking for. They say mathematical notation. Maybe I'm thinking formula. Is there a formula we could write to help us make that happen? Go ahead and hit pause to write it down. Hit play when you're ready to check your work. So I know this was a weird pattern because it wasn't arithmetic or geometric, but I did kind of write a recursive formula. I was like, okay, if I want to know the term, I have to double the term before it and add 1. So I wrote a recursive formula for it. It's not a very pretty recursive formula, but it does the job. Step 3 of the modeling process is to extend the patterns you created, complete operations, make predictions, analyze the mathematical results. So let's push it a little further. So we have this lovely pattern that we came up with so far, but now we know you need to double it and add 1, double it and add 1. Can you finish off the table? How many moves should it take for 4 disks? How many moves should it take for 5 disks? Go ahead and hit pause to write this down, fill on your table, and then hit play when you're ready to check your work. All right, so we said the pattern was, hang on, where's my pen? We said the pattern was that I need to take the one right before it and I need to multiply it by 2. That is the worst. That is the worst ever. That's a really bad 2. We said we need to multiply by 2 and then add 1. So fine. If I multiply 7 by 2, that's 14 plus 1 is 15. Double it and add 1. So multiply by 2. 15 doubled is 30 plus 1 is 31. So theoretically, it should take me 15 moves to win in 4 disks and 31 moves to win with 5 disks. Wow. All right, then. We wrote a recursive formula already. Did that formula help us for finding 4 and 5 disks? I think it did. So I used my lovely recursive formula to help me find the next disks. But here's the real trick. Can you write an explicit formula to represent the patterns shown in your table? That's the trick, right? Recursive is great. It just tells us the next one. Can you get a little creative? Because again, it's not arithmetic, it's not geometric, so you have to get a little creative. Can you get a little creative? And can you represent the pattern with an explicit formula? Give us some thought. I bet you can get there. Go ahead and hit pause to try this out. Hit play when you're ready to check your work. So I gave this some thought and I was like, okay, we keep multiplying by 2, and adding 1, but you know what? I didn't know how to make that an explicit formula. So I kind of looked at it a little bit differently and I thought, you know, I could do 2 to the power of this and then subtract 1, right? 2 to the power of 1 is 2, minus 1 is 1. 2 squared is 4, minus 1 is 3. 2 to the third power is 8, minus 1 is 7. Wait a minute, this works. So I had a hard time with that. And if you had a hard time coming with the formula, that's okay. I struggled with it too. But I realized that if I did 2 to the term number, gives an exponent, and then subtracted 1, I actually did find the minimum number of moves. That was rough. Now, of course, the final step in the modeling process is to interpret your results and test your mathematical predictions in the real world. If your predictions are incorrect, of course, you can just revisit your mathematical work and make adjustments or even start all over again. So we've got our mathematical model, but we want to make sure it works and to test it. So we made a lovely explicit formula. Can you construct a graph to represent your explicit formula and describe the characteristics of the graph in terms of the situation? Label your graph. Okay, can you label your x-axis, label your y-axis? So see if you can graph it and label your x-axis and y-axis. If you need to use Desmos, that's cool. I'm just going to use our table to make my graph. Go ahead and hit pause to write this down to work out your graph, and then hit play when you're ready to check your work. So I just used the points in the table as points on the graph. I was like, all right, the number of discs was my x-axis and the minimum number of moves was my y-axis. So we had 1, 1, we had 2 discs was 3, 3 discs was 7, and we also wrote down that 4 discs was 15, and of course 5 discs took us all the way to 31. So I connected the dots and I have a graph that looks kind of like this. It's not perfect, but you get the idea. So suppose you could make 1 move every second. If you were fast, you were like, choo, 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 choo. How long would it take you to complete a game with 25 discs? You do need to show your work, but I would recommend using that explicit formula we were just talking about. I think that'll be helpful. Go ahead and hit pause, see if you can figure this out, and then hit play when you're ready to check your work. So I went ahead and I used that explicit formula from earlier. D sub n equals 2 to the n power minus 1. Of course, n is the number of discs. There's 25 discs, so I put that in there. Do you remember the magic button on your calculator? Did you remember about that exponent button? I did. So I did 2 to the 25th power courtesy of the exponent button on my calculator, and I got 33,554,432. But I have to subtract 1. So I got 33,554,431. Now, that's the number of seconds, right? And that feels so weird to me. So you know what? I'm going to divide that number by 60. So my 33,554,431, that's seconds. So if I divide by 60, that'll tell me the number of minutes. So I got 559,240.53 going forever minutes. And if I divide by 60 again, that'll tell me how many hours, because there's 60 minutes in an hour. 9,320.65 hours. 675 hours. Oh my gosh. There's 24 hours in a day, so if I divide by 24, I have 388 days. So that's probably why we're not going to play this game with 25 discs, because apparently it would take you over a year to play it. So let's not, shall we? So in this lesson, you used a modeling process to figure out whether the number of moves in the disc game is related to the number of discs, and it was. But the basic steps of our mathematical modeling process, they're just summarized below. We noticed something, we wondered about it, we organized our information, we started making a prediction, we tested it, right? And then, of course, we were able to report on it. So that's all we're doing with our mathematical modeling process. As always, guys, if you have questions or concerns, feel free to email me or come see me during office hours, after lunch, or after school, during lunch, during break. I'm around. And I'll see you guys soon. Bye.